Hey everyone, Mr. Timlin here. Today I wanted to just do a quick video to show you guys a two-body problem example real quick. So let's come up with a scenario. I'm thinking we have two blocks tied together like a little chain, or a little train rather. So let's make two blocks. Well, let's actually make that a little further apart, give myself a little room here. Sorry, my hands are a little shaky. I just had a whole bunch of coffee, so my lines aren't going to be perfectly straight. But we got two blocks tied together. Let's call this mass 1, and let's make it 1 kilogram. And let's call this mass 2, and we'll make it 3 kilograms. That sounds good. And let's say they're being pulled along by a force. We'll call that F1. Let's make that force, I don't know, 20 newtons sounds good. And they're going to be on the ground. We'll call this a frictionless ground. We won't bother dealing with friction right now. That's just going to be more trouble than it's worth. So what are we going to ask ourselves about this? Well, they're being pulled along by this rope here. So let's say that there's some force of tension between them. If they're being pulled along and there's no friction, then that means they're probably going to accelerate as well. So maybe some questions that we have are, what is the acceleration? And what is the force of tension? So let's start going through these. To do the acceleration, to do this first part, we actually don't want to think of them as individuals. We don't want to think of them as M1 and M2. We want to think of it as one large system. Pretend it's just one big block. Like if you're the person pulling it, let's pretend there's just a big box covering this. You can't actually see inside, so you don't know that there's two separate objects. As far as you can tell, you're just pulling this whole system, this whole thing. So step one is to treat it as a whole system. So whole system approach. Let's start by drawing a free body diagram of what that would look like. Well, there's just one force pulling this way. There would be a force of gravity and a normal force pushing up on it. So my system free body diagram is going to look like this. Those two are going to cancel out because it's not going off of the surface and it's not going through the floor, so we don't need to worry about that. And it is being pulled along by one force, F1, which is 20 newtons. Now if this force and this force cancel out, then there's only going to be one force left, this F1. That means that's my net force. So my net force is just F1. Also remember Newton's second law, that my net force is equal to mass times acceleration. This is what we want to solve for. Now let's ask ourselves, do we know what my net force is? Absolutely. It's just my F1. Do I know what my mass is? Yeah, even though we're treating them as two separate, or even though we're treating these two separate things as one object, we know the masses of each of them. So we know what the total mass of the system is as well. So let's use Newton's second law to find our acceleration real quick. I just got to rearrange this a little bit, and I'm going to get my acceleration is my net force over my total mass. In this case, my net force is just F1. My total mass is M1 plus M2. So let's throw some numbers in. F1 is 20 newtons. M1 is 1 kilogram plus M2, which is 3 kilograms. You probably got that quick math done in your head already, but it's going to be 20 divided by 1 plus 3. 1 plus 3 is 4, so that's going to be 20 newtons divided by 4 kilograms, which is going to give me an acceleration of 5 meters per second squared. Per second squared, guys, a lot of people have been saying that the unit for acceleration is just meters per second. That's not the case. That's a unit of velocity. This is per second squared. So we found our acceleration for our whole system. that means we also found the acceleration for each one individually. If that doesn't make much sense to you, well, think about it. Is this block going to be moving differently than this block, or are they going to be moving together the same way? They're going to be moving together the same way. They're going to move together as one. So the acceleration of both of them is the acceleration of each one individually. So getting the acceleration of the whole system, check, no problem. What about my force of tension? If I know my acceleration, now I can find that. And this comes from looking at either one of these individually. So to get Ft, look at an individual object. It doesn't matter which one, both will give you the same answer, and I'm going to do both just to show you. But really, save yourself some time. You don't need to do both. Only one is necessary. It's nice to do both because then you know if you get the same answer both times, then you're on the right track. But let's start with M1. Let's do object 1. Always start by drawing a free body diagram of this object. So maybe I'll do this in blue. Of this object. What are the forces acting on it? Well, there's my normal force and my force of gravity. Those are going to cancel out, again, because we know it's not falling through the ground. It's not being launched upwards, so they're going to cancel. And it's being pulled along. What's pulling it along? Well, there's only one other force interacting with it, and that's my force of tension. So just like we did up here, if I've got this force and this force canceling out, that means my force of tension is my net force. And remember Newton's second law, F net is mass times acceleration. Well, I already know what the mass is, I know what the acceleration is, so that means I can figure out what my net force is. And if I know my net force, well, that's my force of tension. So let's do that quick. F net is mass of object 1, that's 1 kilogram, times the acceleration. Well, I know the acceleration of the whole system, which is the acceleration of each one individually. So that's 5 meters per second squared. What's 5 times 1? Well, that's just going to be 5 newtons. So my force of tension then is going to be 5 newtons. So let's do it with the second object. Let's do this one in red and see if we get the same thing. So this is object 2. This one's going to be a little bit more complicated because there's an extra force acting on it, but you guys should be able to handle it no problem. So let's draw a free body diagram. We have the normal force acting on it. We have force of gravity acting on it, like always. Maybe not always, but in this instance, they're going to cancel out, so we're not really going to worry about them too much. I've got F1 pulling on it, and I've got Ft pulling back on it. We know those two aren't going to be equal because it is accelerating in that direction, so we know F1 has to be bigger. What would my net force be? Well, my net force is just adding up all the forces and see how they cancel out. That cancels with that, so I'm not going to worry about it. So my net force here is going to be F1 minus Ft. Minus because they're going against each other. They're going in opposite directions. And remembering Newton's second law, my net force is also equal to my mass times my acceleration. So let's say this is kind of like a checklist. I know what F1 is. I know what my mass is. I know what my acceleration is. So I should be able to solve for Ft now. So let's do that. F1 is 20 newtons minus Ft equals my mass, which is 3 kilograms, times my acceleration, 5 meters per second squared. So it's going to be 20 newtons minus Ft equals 15 newtons. So you should probably already see where this is going. 20 minus something gives me 15, but rearranging this, I get 20 newtons minus 15 newtons equals Ft, which, big drum roll here, is going to be 5 newtons, which, luckily enough, is the same thing that we got before. So we can put a big check next to Ft and call this problem solved. All right, hope that helps.